testing or so, maybe closer to an hour. So our overall results supported our theorized outcomes. We were able to see improved hydrodynamics with our stepped boat hull when the boat was on plane and running at higher speeds. And then we did see minimal losses in efficiency at our slower speeds, which again was what we were expecting to see. So the results in terms of lift, the slow speeds produced very little difference between the two hulls, which you can see in our test pairs 1 and 3. Those are the two lower speeds. And then the high speeds produced an increase of over 20% on plane and about 17% with our 10-degree attack angle. So both of these are good, and it is what we expected to see, that the stepped hull would produce more lift everywhere in the range. Both speeds also experienced that lower pressure in the steps, which would result in the air being sucked into those pockets and pushing the boat up and lifting the rear of the hull out of the water, again, if we were doing actual testing in water. Results in terms of drag, the slow speeds produced marginally worse drag, again, as we expected to see, because we were increasing the wetted area of the boat's hull. However, the high speeds produced a decrease of over 85% on plane, which that's the number that we really cared about, because that's where these types of boats are running, high speeds on plane up out of the water as much as possible. And so having a reduction of 85% was very encouraging for our results. Now we also saw a 14% increase when we were testing with our attack angle. So when the boat is at an angle like that, we saw an increase in drag, which was expected. We wouldn't have liked to see any, of course, but it was expected due to the increased wetted area. And also that's a very transitory point. The boat does not operate in that point for very long. It's as you're sweeping through your speeds, it would, as you first go, it kind of goes down and then it'll come back up out of the water. So we aren't expecting to be operating in a high speed with an attack angle for long, if at all. So our coefficients of lift and drag, the traditional hull, this was averaged over 2 tests. They were very, very close in terms of each other. So the traditional hull was a 0.012 coefficient of lift, and the stepped hull was a 0.024. For drag, we had the traditional hull being 0.091 and the stepped hull being 0.054. So an increase of 100% for the coefficient of lift on the stepped hull, and a decrease of about 40-ish% on the stepped hull in terms of the coefficient of drag. So our takeaways and relevance to modern society and engineering. This reduction in drag will result in an increased vehicle efficiency. These boats operate right on the borderline of miles per gallon and gallons per mile. So any sort of reduction in drag and increased efficiency in the vehicle itself will have great effects on the fuel consumption and lowering our greenhouse gas emissions. Further testing would allow us to design and come up with better and more efficient step designs, varying different factors, the depth of the cuts, the width, the spacing, number of cuts even, and just overall hull shaping. If this project had greater scope, we would have been able to even increase our results even more. And then an idea that the 3 of us had when doing this testing would be the idea of active step mechanisms for a future project. If the operator of the boat was able to swap between a stepped and a standard hull, you could optimize and perhaps end up with the best of both worlds. Where at slower speeds, you could close down the steps so it was a smoother surface.
I can see that. Have like a sliding hull.
Yeah. And then this also could improve stability in cornering. As Brandon mentioned, the stepped boats sometimes, especially the older designs, suffered in terms of maneuverability and turning. And so improving stability by closing down those steps could be a good safety factor as well.
Any questions, guys? No questions? Good job. Excellent job.